Hey guys, this is Professor Janacek, and I want to talk to you about Extrema. First off, just a real quick review. If we have a function that's defined at some value c, we have a minimum at c if f of c is less than f of x for all x in the domain of f, and a maximum if we have greater than or equal to. We also have something known as a relative minimum. It's the minimum on an open interval, or a relative maximum, which is the maximum on an open interval as well. You might also hear these called local minima or local maxima. Of course, just a real quick review, open interval is an interval which does not include its endpoints. And if you haven't heard the words before, the plural of minimum is minima, and the plural of maximum is maxima. And so if we take all of the minima and maxima of a function, we call them the extrema. And that's what we want to look at today. Now, first off, when dealing with extrema, we're going to have to determine the critical numbers. So critical numbers will begin by letting the first derivative, f prime of x, be equal to 0, or we'll let the first derivative, f prime of x, be undefined. The x values that give us 0 for the first derivative or undefined for the first derivative, those x values are the critical numbers. We often refer to those as c, just to make it a little easier. And then in order to determine an extrema, we actually have what's called the first derivative test. So for the first derivative test, we'll take an L value, which is to the left of our critical number on the number line, and an R value, which is to the right of our critical number on that number line. So we pick a value to the left and a value to the right. We do need to make sure that there's only one critical number between those two numbers that we picked off the number line. Now here comes the fun. If f prime of L is less than 0 and f prime of R is greater than 0, then what we have is a relative minimum at the point C, f of c. And if f prime of the number to the left, L, is greater than 0, and f prime of R, the number to the right, if that one is less than 0, then it turns out there is a relative maximum at C, f of c. Now, if we don't have both of these conditions, if we don't have those two setups, then we say that there is no extrema at that point C, f of c. Let me just explain what's going on here. If you recall the first derivative, f prime of x, if this is if this is less than 0, then f is decreasing. And if the first derivative is greater than 0, then our function f is increasing. So, big thing to remember here is that the first derivative gives us increasing or decreasing. Again, the first derivative tells us if our function is increasing or decreasing. So, looking at these situations here, the first derivative on the left-hand side is less than 0, and the first derivative on the right-hand side is greater than 0. What we have going on is that on the left, less than 0, it's decreasing, and on the right, it's increasing, it's greater than 0. So that would give us a minimum, as you can see here. Now, the other situation, if the first derivative on the left is increasing, and the first derivative to the right is negative, which is decreasing, and now you can see we would have a maximum. So that's the situation. Now, if you have negative, the first derivative is negative on both the left and the right, decreasing and decreasing, that does not give us an extrema. Or if they're both positive, increasing and increasing, again, that does not give us an extrema either. So those don't do anything for us. All right, well, let's take a look at an example here. Suppose f of x is equal to e raised to the negative x squared. So notice the negative is not squared, it's just the x that is squared. First thing I like to do is go ahead and figure out, well, what is f prime? Let's take a second and calculate f prime. That is e to the negative x squared. Remember, we're going to use the chain rule here, so then we would have to take the derivative of that negative x squared, which gives us e to the negative x squared times the derivative of negative x squared is negative 2x. So we end up with negative 2x e to the negative x squared. All right, there's our first derivative. Now, let's go back and figure out what our critical values are. We are going to use that first derivative when the first derivative is 0 or undefined. So let's see. Let the first derivative be equal to 0 or be undefined. So what do we have? The first derivative is negative 2x e to the negative x squared. That's equal to 0. Well, if that's the situation, remember e raised to any power is never 0, so that gives us negative 2x is equal to 0, or x is equal to 0. Now, for the other one being undefined, this is one that people often forget to do, so don't forget about this one. We want to do the same thing, but now look at when is this undefined. Well, it's not as hard as it might seem. Remember that e raised to a negative power is really that same thing, but in the denominator. So when is this undefined? Well, that would be, this one is undefined when the denominator, e to the x squared, is 0. But this never occurs. E raised to a power is always a positive value. All right, so our only critical value came from when the first derivative was 0. So our only critical value is x equal to 0. All right, well now let's go ahead and pick our values to the left. We're going to, use the first derivative test. So we will let L be a number to the left of 0. So let's take negative 1. And R be a number to the right of 0. Let's use positive 1. Then we have f prime of negative 1. So the first derivative, again, I'm looking at the first derivative, not the function yet. First derivative evaluated at negative 1, negative 2 times negative 1, e to the negative times negative 1 squared. Simplify all this, that gives us positive 2, e raised to the now negative squared is a positive, but then there's that other negative, so that ends up being something like this. Notice this is 2 over e. E is a positive value, so we know this whole thing is positive. All right, so we know that f is increasing. Since this first derivative is positive, the first derivative tells us increasing or decreasing, greater than 0, increasing, and that is to the left of x equal to 0. Well, let's also take a look at what happens to the right. Let's take the first derivative at 1, our value to the right. Again, I'm using the first derivative. I haven't gone back to the function f yet. I'm looking at f prime. So in this case, oh gosh, this is getting, here we go. In this case, we have negative 2e2. Again, 1 squared is 1, but there's still that negative. So we have negative 2 over e, which of course e is positive. With that negative in the numerator, though, that gives us a negative. So that means f is, since the first derivative is negative, then f is decreasing to the right of x equal to 0. All right, so what do we have here? Well, we have increasing to the left, decreasing to the right. Thus, looks like there is a relative maximum at x equal to 0. Now, you could also say at the point. Now, remember, we would have to figure out what the function value is at 0. Notice my y value here would be f of 0. And so here we would have to go back to our function, not the derivative, if we want to find that y value. And in this case, we would have e to the 0, but anything raised to the 0 power is 1. So you could say that we have a relative maximum at the point 0, 1. And there you go. Enjoy.